Okay, so by now we are super familiar with the Canvas page, I hope. So I just wanted to point out a couple things here. So the exam 2 topic list is right at the top of this one. So if you click on here, it should give you a list of the topics for tomorrow's exam. So remember, we're going to finish 3.7 today, but whatever we start in chapter 10 will not be on exam 2, okay? It will tell you how the questions are going to be in order. So when you get to the test, after you do your statement of integrity and after you do your reference sheet, the first question should be a question on inverse function. Okay, so it's just going to kind of go down the list. That way you kind of know how to plan your time a little bit for your exam. Okay. I would really encourage you to look at that, especially when you're making your reference sheet. I think maybe if you know it's going to be in that order, putting your reference sheet in that order might even be pretty helpful for you, okay? All right, the other thing I wanted to show you was that extra credit opportunity, okay? So I'm just going to click on this extra credit opportunity here. And you've got the extra credit for this exam is really around shoring up our factoring skills. So there's 3 different activities that you can do here. One is on Desmos. It is not as long as the one we did on Monday, so I don't want you to be scared and think like, oh gosh, I'm gonna have so many things. I think it's like 8 different slides, and it's a lot more interactive where you can move things around and it will tell you whether things are right or wrong. So it's a lot less kind of hoping and clicking randomly and like, oh, I hope this is going to be correct, but it actually does tell you whether it's correct or not. Okay, so that's one option. You can also watch my factoring by area video and then send me, there are 3 practice problems at the end. You can work those out and then email those to me. I think, and then the last one is factoring by grouping. So if you're like, I don't really like this factoring by area, but I want to try a different way, you can check out this video by Patrick JMT. And he does a great job explaining the factoring by grouping. Now, I actually sent you, I linked to this particular video because I think that this individual on YouTube actually has a lot of great resources in terms of any of the math that you'll probably be taking in the next year. So, you know, I think one of the things about this remote learning or really taking any class is thinking about what kind of outside resources you can find for yourself. And so if you find a YouTube channel that you like, then that's probably a really helpful thing early on. Okay, so I just wanted to kind of expose you to his YouTube channel, see what you think. If you like his style, he has a ton of videos and he does a bunch of stuff for Calc 1 as well. Oops, I didn't change this deadline, but email all your work to me by tomorrow morning, Thursday, September 17th at 9:30, okay? So I just wanted to remind you of those extra credit opportunities as well as help to prepare for the exam. Are there any questions on that so far? Okay. Let's see. Okay, so what we're gonna do today is we're gonna finish up 3.7. So I know that we kind of spent a lot of time at the beginning of class, more than I intended, but some time at the beginning of class sort of exploring the ideas of when a vertical asymptote happens or when a hole happens. And then we had a chance to work through one question together. But what we're gonna do today is finish up that other question, which should hopefully help clarify the second question of that type on quiz 9, okay? And then we're gonna actually spend some time doing a group work, a small classwork assignment for today, and that classwork assignment will be very similar to the one of the questions on quiz 9, just to make sure that, you know, as we're moving into the exam tomorrow, that you get a little bit of extra practice and it's something that you feel confident doing, okay? All right, so I'm gonna go ahead and share my screen. We'll go back to the 3.7 notes part 2, okay? All right, so let's kind of see where we were at. So we spent some time at the beginning of that class on Monday looking at graph transformations and how they apply to new characteristics, including a vertical asymptote or a hole. And then one thing that folks asked questions about was like, how do we know if there's going to be a hole versus a vertical asymptote? And so we hopefully clarified that the hole is when you have a common factor in the numerator and the denominator, whereas a vertical asymptote is only going to be in the denominator, okay? So that vertical asymptote only happens when the denominator equals 0, whereas the whole happens when the factors in the top and the bottom, okay? And then we talked about end behavior. We talked about end behavior. And let me scroll up so you can see that end behavior piece, right? Where we had to compare the degrees of the top and the bottom to come out with whether we have a horizontal asymptote or not, okay? One thing that I did want to clarify here is this. When we have a horizontal asymptote, okay? When we have a horizontal asymptote, do you see what title it's underneath? It's underneath end behavior, okay? And that's not a mistake. It's not like, oh, instead of calling it a horizontal asymptote, I named it end behavior by accident, okay? It's actually very intentional because when a function flattens out at the ends, okay? So when a function flattens out at the ends, meaning it doesn't go up and it doesn't go down, it just kind of goes flat. So when a function flattens out at the end, we know the function has a horizontal asymptote, okay? So if you think about quiz 9, there was that one question, I think it was like 7 and 8, where they asked us to find what the end behavior is, okay? So if someone says find the end behavior and you know there's a horizontal asymptote, that means your end behavior is the horizontal asymptote. That's what happens at the end. It flattens out, and it flattens out to a number, okay? So when we have a horizontal asymptote, that is actually our end behavior, all right? But what makes these discontinuities different is discontinuities, they usually happen in the, let's call it the interior or the inner parts of the function. And since they happen in the interior parts, they are not considered end behavior. Okay, because they happen on the inside of the function, not like what happens at the very ends of the function. Okay, I just wanted to clarify that before we did that. Yeah, so no worries if that was a mistake that you made on the quiz. I just want to make sure you're clear on it for tomorrow, that when I say end behavior, it could be up, down, or it could be a number if your curve flattens out, okay? Okay. So then we did this example together in class, and it was a long example. It kind of took us a while. And there were hopefully some good connections that we made between how we find an x-intercept, how we find a y-intercept, how we find the discontinuities. That if we have the discontinuities, they actually tell us what the domain is, okay? And it's okay to have more than 2 sets of those brackets for interval notation. You can have as many as you need, and they all kind of match up to the different parts of the function, okay? And just to really drive home that point from earlier, if we look at this last question here, it says, determine whether it has a horizontal asymptote or a slant asymptote. And we knew on Monday that it had a horizontal asymptote of y equals 0, but another way I could ask that question is, what is the end behavior of your function? And you would say y equals 0, okay? So same answer, different way of asking the question. And so what we're going to have a chance to do in just a little bit, I made a question that's very similar to number 1, okay? And you're going to be able to work on that in groups, and you can think about that as just like a good practice problem for tomorrow's test, okay? So after we go through example 2, we'll split up into some small groups, and you'll have a chance to work through another version of one that's like example number 1, okay? Now, before we do that, we're going to go ahead and try this example, okay? And so this one is very similar to question 7. This is, 8, similar to number, 7 on quiz 9. Okay, so this one is similar to number 7 on quiz 9. Now, I do want to say that this question right here, so this version, like the way we ask the question in example 1, that's what I'm going to look for on tomorrow's test, okay? I want to do this second example because I want us to think about how all the things are actually connected together, all right? And to know that you can see a picture and actually read all this information from it, okay? So think about this example less as like the kind of question you're gonna see on tomorrow's test, but a good way to practice understanding the concepts behind that, okay? All right, so let's begin. We've got this graph. Let me expand that a little bit for you. So we've got this graph, all right? Someone tell me about the end behavior of this function. What is the end behavior of this function? And how do you know? Okay, so what is the end behavior and how do you know? Yeah, it's going to be at y equals -4. Exactly, exactly. Okay, so y equals -4. Now we can almost go ahead and just say, oops, change the size of the highlighter there. We're gonna go ahead and say this is our horizontal asymptote, but it is also our end behavior. Okay, now that means I'm gonna go down to the very bottom box where I ask about the end behavior, and I'm gonna fill in this information. Okay. So it says determine whether the rational function has a horizontal asymptote of y equals 0, y equals a number, or a slant asymptote. And in our case, we have, there is a horizontal asymptote at y equals -4. So we can say that the end behavior is y equals -4. Okay, so those two statements are equivalent. Now, what does an end behavior of negative y equals -4 or a horizontal asymptote at a number, what does that tell us about the top and bottom of our rational function? Okay, so what does a horizontal asymptote at y equals a number tell us about our original function? Yeah, the degrees are the same on the numerator and the denominator. Exactly, exactly. And I love how quickly everyone was able to explain that. So we know that the degree up here, so we have our degrees are equal. Now we don't know what they are yet, but we know the degrees are equal, okay? But we also know something about the leading coefficients. What do we know about the leading coefficients? Ah, okay, yes. So Ethan, let's modify that just a little bit. The top divided by the bottom, the ratio of those equals to -4, okay? So the ratio of the leading coefficients equals -4. So for example, it could be like -4x² over x². That would work out, okay? It could be 8x³ over -2x³. That would also be okay. All right, so it doesn't necessarily mean that the top or the bottom has any given number per se, but the ratio of the top leading coefficient and the bottom leading coefficient should be equal to -4. Okay, so that's all the stuff that we can tell just from a horizontal asymptote on the graph. There's actually so much information that it tells us. Okay, so let's go back to our graph. And let's take a look now at the discontinuities, okay? So remember, there are two types of discontinuities. One where you have a number divided by 0, and a second case where you have 0 divided by 0. So which one or ones do we have in this particular function? Yeah, we have a whole and we have a vertical asymptote. Okay, so let's highlight both of those. Exactly, the vertical asymptote is going to come from number over 0, whereas our whole came from that corresponding factor in the top and the bottom. So let's see what we have for our vertical asymptote. Okay, so we have a vertical asymptote at x equals 4, okay? And we have a whole at x equals 2, okay? Now, one thing that I did see on just the small handful of quizzes I had a chance to look at before we started class is that some folks are saying the whole and giving like a coordinate. And so I saw some people who might have answered this as like 2, 6, okay? Now, I know there are some resources out there that give you the entire point, like the x and the y. But I think one thing that tends to happen as you move a little bit higher in math is if we know there's a whole, we typically only give the x coordinate. Okay, so we say like, if x were this value, like that's where the whole is. Because there's not actually a point there, we don't actually give the y value because it's not actually the point, okay? If you did that on the quiz, that's totally fine, but most of the times folks say, oh, there's a hole at x equals 2, or there's a hole at x equals whatever number it has to be, almost in the same way we talk about the vertical asymptote, okay? So after we've figured these two pieces out, we know that the vertical asymptote tells us about the discontinuity from the number divided by 0. So vertical asymptote at x equals 4. So what is the corresponding factor that goes with x equals 4? X minus 4. Good, good, good. So that means that x minus 4 is a factor of the denominator, g of x, okay? And we knew our hole was at x equals 2. So hole at x equals 2. Its corresponding factor is x minus 2. And we know that is a factor of f of x and g of x. Okay? So we've got our vertical asymptote, we've got our hole. Guess what we can do right now? And we could have done this just from the picture. We can go ahead and write our domain, okay? And so in this case, how many different sets of parentheses should we have for our domain? Like just like one set of parentheses, 2, 3, 4, like how many do we need? All right, Thea says 3, Richard says 3. Okay. Now, it might be easy to look at the graph and be like, oh, 2, because there's the left branch and the right branch, right? But I think the thing that Thea and Richard both picked up on, there's that hole, and we have to excuse that point as well, okay? And so what we're going to do is we're going to start with from negative infinity. The next point that we have to take out is the 2. And that was our hole. In union with 2 to 4, right? So 2 is the hole that's missing. That's why we have to use parentheses there. And then our vertical asymptote also gets excluded in union with the other side of the asymptote. Okay? So that's how we write our domain here, all right? Now, when we're looking at the domain though, I've had students in the past ask, and I'm not sure if anybody has this question, but just in case you do and you didn't want to ask it, some students are like, well, how come I can't just put like not negative 3. How come I just can't put negative infinity to like 3 and it say like I'm including 3, because 3 comes after 2. What's wrong with just changing the 2 to a 3 and saying, oh, I'm going to include that? Yeah, I'm still including the 2. Okay. So then I've had other students who are like, well, if I can't include the 2, I'm going to put a 1 here because 1 is smaller than 2. What's wrong with having a 1 there? Yeah, there's a whole bunch of values between 1 and 2, like 1.1, 1.9, 1.5. There's an infinite number of values that you're leaving out if you don't say, let's go right up until we go to 2 almost. And that parentheses is that almost part, okay? So we're going almost up to 2. We're taking a small break for the whole, and then we continue on the other side of 2, all right? And we do the same thing when we get to the vertical asymptote. We pick the one side of the asymptote and then the other side of the asymptote, okay? I want to take a moment here. Not right now. We're going to come back to this before I send you off to do your classwork, and we'll talk about the domain of inverse function. Okay. I'm going to talk about that real briefly before I send you off to do some group work, okay? All right, so we've got factors, we've got ratios of leading coefficients that we need to include. So we can actually go ahead and start to write this function. All right. Now, I know that I have x minus 4 only in the denominator because that's where the vertical asymptote is. I also know that I have an x minus 2 on the top and the bottom. Now, you do not have to line them up like this where they're like one right on top of the other, but you can, if that helps you remember, okay, I've got a hole here, and then I've got the vertical asymptote, right? So like this is our vertical asymptote, and this gives us the hole, right? So far, we've achieved the hole and the vertical asymptote. Do we have the right end behavior? Do we have the correct end behavior? All right, Hillary, what is, or Goretti, what is the end behavior of the current f of x? Like the way I wrote it right now, what's the end behavior there? That's okay. All right. So for the folks, yeah, Hillary, that's exactly correct. The way I have it written right now, the degree on the top is smaller than the degree on the bottom. So this is going to give us a horizontal asymptote at y equals 0. Okay. Because the degree on the top is 1 and the degree on the top is 2, or on the bottom is 2. And so that is going to be when we have the horizontal asymptote at y equals 0. Okay, well, what do I need to do in order to get the degrees to be the same on the top and bottom? Because that's what we said earlier. We said the degrees on the top and bottom have to be the same in order for us to divide those coefficients. Yeah, exactly. Oh, sorry for that, Richard. Yeah, the degree of the degree of the numerator and the denominator need to be the same. Okay, so let's look at the x and the y intercepts. Okay, which one of these, the x or the y intercept, give us a factor on the top? All right, we've got two conflicting answers here. We have one who says the x and the other who says the y. So let's go back up for a moment and take a look at the x and y intercept stuff that we did on, no. Technology fail, hold on. Okay, so let's go back up and look at example 1 for a moment. Which one of those gave us the x, or I'm sorry, which one of those gave us the factor in the top? Yeah, it's going to be the x-intercept, okay? So that was sort of this light purple color we used on Monday, where we said when we want to get a zero out of a fraction, then the top has to be equal to zero, okay? So we're going to use that idea to help us figure out what is that other factor on the top, okay? So let me scroll back down. Okay, so we know that we have a whole at x equals 2. And we also, if we zoom in here, we've got an x-intercept at -1, 0. So if -1, 0 is the x-intercept, what is the factor that goes with that? Okay, so if -1, 0 is the x-intercept, what is the factor that goes with that? Yeah, x plus 1. Good, good. You guys really got that factor theorem down. That's really good. Okay, so guess what we found here? Let's use our light purple color. X plus 1 has to be a factor on the top. Okay. So that's how we find the other factor. It's not like we just kind of make one up and we're like, well, I don't know, I'm just going to plug in the numbers afterwards and see if it works out. That can be a very frustrating way to approach the problem. But what we're trying to do is say, they gave us all these points. They must mean something. And it's really up to us to figure out how they're all connected. Okay? All right, now they do also tell us the y-intercept. They tell us that the y-intercept is 0, 1, okay? Does this right now, the way our equation is written, does this match every single piece of information that we've written down about our function? All right, Ethan says everything but the horizontal asymptote. Yeah, and Richard, I think you bring up another really good point. When we plug in 0 for x right now, you don't get 1 as the output, okay? So we need to fix something here. There's one last piece to this puzzle so that we can make our equation match our graph, okay? So let's go back to the y-intercept for a moment, and let's just plug in 0 into the equation we have right now. So f of 0 equals 0 plus 1, 0 minus 2 over 0 minus 4, and 0 minus 2. Okay, so right now we're getting -2 over 8. But we don't want -2 over 8. We just want a 1. What is -2 over 8 reduced to? -1/4. How do we make a -1/4 into a 1? folks are saying times -4. Okay, so let's see. If I multiplied by -4, that would mean I would take my -1/4 times -4. That would make the numerator equal to 8, and 8 over 8 will give us 1. Okay. Now let's just double check the other piece. Do we get a horizontal asymptote or end behavior at x equals -4? But y equals -4, sorry. All right, are the degrees the same, and do those coefficients divide to give you a -4? No, Gloria, we're gonna multiply by -4, because if we add like a did you mean, do we like put it in the top like a -4, or do you literally mean like add? Okay, we put a -4 in the numerator, but we put it there as a multiplication for everything so that we can get the right y-intercept. Okay. Does this help clarify this kind of problem a little bit more? And sort of like the story that we're going for here? I know that might be the nerdiest thing that you've ever said, well, so far, but yeah, it is pretty amazing how things work together, okay? All right, so again, this example is something I really wanted us to do so we could sort of understand like where all this stuff comes from and like how we need to make things fit together, okay? But on tomorrow's exam, we can expect something that looks a little bit more like example number 1, okay? So what I'm going to do right now is I'm going to stop sharing my screen, and I'm going to ask folks to go to Canvas, okay? So if you go into Canvas, and I'll show you where to find it too, okay? You go to the home page, that's where everything is. There's not a lot of fluffy things here going on. Like I know a lot of other instructors have like really cool fun pages. Mine is not cool and fun, but it is very functional. Um, so where you're gonna go is if you go into the assignments, okay? And you're gonna go down until you see classwork number 10, all right? So we're doing classwork number 10. You're gonna click on classwork number 10. So you're going to go to classwork number 10, and when you click here, it should bring you to a Google Doc, right? See how many folks are on there right now. No one. Okay. Is everybody able to find the, oh, there you all are, classwork number 10. Okay. So you see how this one is like pretty similar to question number 1, right? It's got the x-intercept, y-intercept, but they give you the equation first, and then they want you to answer all the pieces. Now, one modification to the graph. I do not need you to draw the whole graph. That was something we said we didn't really need to go to that level of detail. But I would like to see the characteristics. So for example, if you find an x-intercept, I want you to plot that on the graph. If you find a y-intercept, I want you to put that on the graph. If you find a vertical asymptote, I want you to draw that. If you find a hole, I want you to draw that. And if you have a horizontal asymptote, I want you to include that on your diagram. But you do not need to connect the dots, okay? No connecting necessary, just put all the different characteristics on there, okay? So let's go ahead, and you've all found your way there, which is excellent. Let's do, how much time do you think that'll take us? 10 minutes? 15 minutes, 5 minutes, 10-ish. All right, so let's do some quick breakout rooms for about 10 minutes, okay? And then what we're gonna do is you can work on it together, but I want each person to submit their own. Okay, so each person should submit their own. And after class, I'm gonna post an answer key for this. I know I don't always post answer keys for classwork stuff, but I think because we have the exam tomorrow, I just want you to feel extra confident that your answers are correct. Okay, so we'll do the classwork, you'll turn those in, and then I'm gonna post an answer key so that you can check your answers for that. Okay. All right, so off we go. Nope, wrong way. All right, folks, I will see you back here in a little bit. Remember, you can raise your hand, ask for help, and then I can pop in. If I don't pop in right away, I'm probably in a different room helping someone else, so I'm not ignoring you, but I will be with you as soon as I can, okay? So one thing about the graph transformations is that if the functions are a little bit more complicated, like the rational functions, it's not always as clear, like, oh, this number does this and this number does this. Because you almost have like two different polynomials where like something is happening here and then something else is happening down below. And so together they create the whole function. So it's not as cut and dry as a lot of the other graph transformations that we've been used to with more of the simpler cases. Is that the question that you're asking, or am I misinterpreting that? Ah, okay. So yeah, it's definitely more complicated in the sense that if you have a minus sign, it doesn't necessarily mean certain reflections. It really depends where that sign is. If I had a negative sign in front of the whole function, then that would take whatever function was inside and reflect that. But a minus sign in the middle of all these other equations doesn't necessarily mean a reflection. Okay. I think to kind of better answer that question, I forget who it was who asked last time, like, how do we know if it goes up next to a vertical asymptote, or how do we know if it goes down? That's a little bit more of a complicated question, but we can kind of just plug in numbers to see. Yeah, I think it was you as well. Okay, so the bottom line is you can't necessarily use all the graph transformations that we've used so far to kind of construct this. We're taking it almost like a little step further and then thinking about more like how do we match every single piece of the puzzle. Okay, I love that you folks are asking these questions, though. I think they're really, really valuable. Okay, so let me just share my screen for this one last example before we go on break. Okay, so this is a fairly simple example, but I wanted to review very quickly, like how do we find that inverse function, but also how do we find the domain of it. So one thing to keep in mind is when we talked about inverse functions in the beginning, we knew that we had to switch the x and y's, right? That was sort of like the foundation of what we did to get an inverse function. And when we're switching x's and y's, we're really thinking about reflecting it over that line y equals x, okay? But one of the things we need to think about is in order to reflect a point, there has to be a point there to reflect. Meaning, if I have a function And let's just say I had like an exponential function, but I had a hole in it. If I want to reflect this over that line, y equals x, when I reflect it, the hole is still going to be there. Does that make sense? Like conceptually, like if there's no point there to begin with, when I switch my x's and y's, it doesn't matter for the inverse function because that point still will not be there. Okay. And so for this reason, when we think about the domain, okay, of the inverse function, we need to think about what is the domain of the original function, because that carries over, okay? So one thing that I kind of do right off the bat so that I don't make a mistake is I say, what is not in the domain of my original function? And in order to do that, I can take my denominator, set it equal to 0, just like we've been doing with these rational functions. So I know that this function has a vertical asymptote at x equals 3, okay? Because I set 3 minus x equal to 0. Now, what else does that mean? That means that x equals 3 is not in the domain of f of x. Does that make sense? Like if we have a vertical asymptote, then x equals 3 is not in the domain of the original function. But what that also means is x equals 3 is also not in the domain of the inverse function. So when I get to my answer, I want to make sure x equals 3 is also not in my answer for the domain. Right? So before we actually go through how to like switch the x's and y's, can I just like, if you have like a, yes, this makes sense to me, like I need to exclude this from my domain, or no, I'm still not really sure what you're talking about, that would be super helpful. I think you can even do like fancy like thumbs up and stuff in here. Okay. Yeah, Brian, that's a really great way to say it. So all previous restrictions have to be preserved in the inverse, okay? So if it makes sense for you to sort of like write this out to yourself, you don't have to write nice fancy sentences, but you can just make a note that like this is not going to be in the domain of your inverse function, okay? So now let's get to finding the inverse, right? So to find the inverse, we're gonna write it as y equals x plus 6 over 3 minus x, right? We're gonna switch our x and y, so x equals y plus 6 over 3 minus y, okay? And I know that step is something that everyone knows how to do, right? That everyone is like, all right, I know an inverse, I gotta switch my x's and y's. But a lot of times when people get to this step, they're like, I don't know what to do now, especially like in the moment of panic on a test, right? So what do we do from here? All right, yeah, we take that denominator, we multiply both sides by 3 minus y. And so that's going to give us x times 3 minus y equals y plus 6. Okay. Now, I've even seen students get to this point and they're like, all right, I know I need to multiply that denominator. Here we go. And then they're like, oh my gosh, I don't know what to do. There's so many letters and they're mixed together. Okay. What do we do from here? How do we make this better? Okay. So we do want to get the y's all on one side together. Okay. So how do I move the y back in? Okay, so Christina says distribute that x. Good. This is a really important step. Okay. I've seen students at this point not distribute. They don't want to make it messier. They're like, why would I start to mix my x's and y's? They're like, well, if I want to move the y back over, then I just divide both sides by 3 minus y. Okay, now I'm writing that in red because it's not mathematically wrong. It's totally valid to do that, except that all you did was create a cycle that you can't get out of. You're going to multiply by the 3 minus y, you're going to divide by the 3 minus y, you're going to multiply by the 3 minus y, you're going to divide by the 3 minus y. And then you start to panic because you're like, I cannot get the y's like all together, like just one y, okay? So instead of panicking, we are going to do what Christina said. We're going to distribute that x. We're going to take that left-hand side and make it messier, okay? We're going to make it messier and then it will get better. So we'll get 3x minus xy equals y plus 6, okay? What do we do from there? And I think, Antonio, you kind of hinted at this already. What terms do folks want to move? So I really like the way Antonio's framing this in the chat. He says you want to move the y's to one side, okay? That means that you have a choice. You can move all the y's to the right side, or you can move all the y's to the left-hand side, and it will not matter. You'll get the same answer. But you have this term with the y, and you have this term with the y. So all the things in green need to be on the same side as each other, but all the things in the blue, those need to be on the other side, okay? So let's go ahead and I'm actually not going to do what Richard said. I'm going to do the opposite. I'm going to subtract the 6. I know, I'm going to tell you why. I'm going to subtract the 6 and I'm going to add the xy. You should be. It was a bad decision. I'm just kidding. Are we at that stage yet? Okay, so here's why I don't want to subtract the y. It's not mathematically wrong, and it's totally fine to do that. But if you add the xy and you subtract the 6, you'll end up with mostly positive terms. You'll get 3x minus 6 equals y plus xy. And I think for some folks, just having fewer negative signs makes the anxiety a little bit better, if that makes sense. Like, I think we tend to panic a little bit more when we see negative signs. And here, in this case, we've created a situation where we can avoid the thing that we don't like. We can avoid the minus signs, okay? Now, I don't want to put this in red because it's not wrong. It's actually also correct. Let's do this in the green. Let's say we did what Richard did. 3x minus xy equals y plus 6. So Richard said subtract the y and subtract the 3x. So then you're going to get negative xy minus y equals negative 3x plus 6. Okay, so negative xy minus y equals negative 3x plus 6. The thing in the green is absolutely correct. But sometimes when we see those minus signs, we're just like, oh my gosh, what am I going to do now? Like, and we just don't see the path quite as clearly, okay? So let's solve both of these and show that we can actually have two different looking answers, but they're actually the same, okay? So over here in the one that has no negative signs, I can factor out the y. So I get 3x minus 6 equals y parentheses 1 plus x, right? Can someone tell me why that's a 1 plus x? I know, right? All right, why is this a 1 plus x and not like just x on the inside? Yeah, we factored out the y, right? So we need a placeholder for that. And then we can divide and we'll get y equals 3x minus 6 over 1 plus x. And we would replace that with our inverse function equals 3x minus 6 over 1 plus x. Okay? Now, if we did the same thing with the one in the green, we could factor out the y, and we'd be left with negative x minus 1, which equals negative 3x plus 6. And then we could divide, and we would get y equals negative 3x plus 6 over negative x minus 1. These two are equivalent, all right? These answers are the same, and we can kind of see that because all the terms are the same, but they all have opposite signs. Okay, so you see how like the inverse function with the positive numbers, that was a 3x, but in the other method, it's a negative 3x, right? So same term, but opposite signs. And then that plus 6 and the minus 6. The plus x and a minus x, a plus 1 and a minus 1. Okay, so if every single term is the same, except every single term has the opposite sign, you're still fine. You still have the right answer. Okay. I will not mark you down for having the answer in the green. That's mathematically correct. But I think as we think about ways to make our lives easier, we want to think, okay, what's easier if it's positive? And sometimes it might not really matter. Okay. But the whole point of this question was really to talk about the domain, right? So we said initially, and we don't want to forget that x equals 3 is not in the domain. And we need to carry that all the way through until we get to the end, that we know x equals 3 is not in our domain. What else is not in our domain? So x cannot equal 3. What else can x not equal? Yeah, x cannot equal negative 1, right? And we know that because negative 1 will make the denominator equal to 0, all right? So x cannot be negative 1 and it cannot be 3. So when we write it out in interval notation, we go from negative infinity to negative 1 with negative 1 to 3 with 3 to infinity. Okay, and so the 3's are from f of x, and the negative 1's are from the inverse function. Oh, Brian, crack me up. Um, I mean, look, mathematicians at the end of the day are pretty lazy. We don't like to write more than we have to. We don't like to do more work than we have to, which is why there are all these different shortcut methods. What do you mean about 6? Why not? Why can't x be 6? Why can't it be -6? Like, what part of the equation tells you it can't be -6? Were you thinking because we have this -6 up here? Okay. Well, I'm glad you figured. Oh, okay. Were you looking at the wrong problem? Okay. Well, I'm glad you figured it out. But I hope this was a helpful review of like inverse functions and domain, because I think sometimes we think domain is only for one thing, but the reality is we use domain for a lot of different things. Okay. Okay. So I'm gonna go ahead and, oh good, I'm glad. I'm gonna go ahead and stop the